Hello everyone and welcome to the next video in the series. In this video, I will take up the topic of radiation formulas. Now, radiation has to do with a certain kind of isotope. And just as a reminder, isotopes are atoms with the same number of protons, so they are the same kind of atom, but they have a different number of neutrons. As an example of some of the isotopes of carbon, we have C12, which has 6 protons and 6 neutrons. C13, which again being carbon, it has to have 6 protons. And 13 is the total number of protons and neutrons. It's the mass number. And so if we subtract 6 from 13, we'll end up with 7 neutrons. C14 again has 6 protons because it's carbon, and to find the number of neutrons we can subtract 6 from 14 to get 8. So this particular isotope C12 has 6 neutrons, C13 has 7 neutrons, C14 has 8 neutrons, and these are the different isotopes or some examples of the different isotopes of carbon. Now, some isotopes are referred to as radioisotopes. And these are isotopes with an unstable nucleus. And a nucleus is unstable, or any system is unstable if it doesn't stay what it is as time goes by. At some point, changes are observed in that system. And the isotopes with unstable nuclei have nuclei which are unstable. And as time goes by, they change in some way. And the way they change is by throwing out particles from the nucleus. And depending on what kind of particle they throw out, we classify them based on that. Examples of isotopes with unstable nuclei are C14, the particular isotope of carbon, which is C14. Iodine 131 is one that's used quite frequently in treating problems with the goiter gland. Technetium 99M is another one. And as I just mentioned, the type of the radioisotope is based on the kind of particle that it throws out of the nucleus. As an example, alpha radioisotopes. These are radioisotopes, isotopes that throw a grouping of 2 protons and 2 neutrons from their nuclei in order to become stable. Beta radioisotopes throw an electron out of the nucleus. This electron is generated from the splitting of a neutron into a proton and an electron. The proton stays behind in the nucleus, and the electron is thrown out at high speed, close to the speed of light. Gamma radioisotopes throw out a photon, and there are others. As an example of these radioisotopes, we have carbon-14 changing into nitrogen-14 plus an electron. Carbon-14 is a beta radioisotope, and keep in mind, in a beta radioisotope, a neutron in the nucleus splits into a proton which stays behind. That's how carbon becomes nitrogen, because we end up with 1 more proton. From 6 protons, we move to 7 protons, which means that carbon changes into nitrogen. And the electron that's generated from the splitting of a neutron into a proton and an electron is thrown out at high speed. The entity that's thrown out at high speed is referred to as radiation. Now, as far as the behavior of radioisotopes go, we know that after a fixed length of time, which we refer to as the half-life of a radioisotope, half of any given sample decays. The particular length of time depends on the particular radioisotope. For some, it may be a fraction of a second. For others, it may be a few seconds, or a few minutes, or maybe a few hours, days, years, or even thousands or millions of years. So there is a wide range of time scales. But whatever the length of time for the particular radioisotope that you're looking at, let's say, for example, 8 days, every 8 days, half of whatever you have decays. By decay, we mean that it changes. For example, in this nuclear reaction that you see here, carbon decays into nitrogen. This actually is the case for iodine-131. Half-life is 8 days. And so that means that if you start with a sample of iodine-131, after 8 days, half of what you started with decays. If you start with, let's say, 100 grams, after 8 days, you will have 50 grams. If you start with 20 grams, after 8 days, you will have 10 grams left. Now, this behavior is going to lead us to the formula for radiation. And this formula, with m0 being the initial mass that you start with, m being the final mass, and n is the number of half-lives passed, will be m equals 1 over 2 to the power of n times m0. Let's see where the formula comes from. And here on the right side, I have a table of values with n being the number of half-lives that have gone by. M is the final mass. And before any time goes by, we start with the initial mass m0. After one half-life, we will have half of m0 left. Now, one half-life, again, how long that is depends on the radioisotope. For iodine-131, it would be about 8 days. For carbon-14, it would be close to 6,000 years. And so one half-life, the duration is not under discussion here. The key is that after one such period of time has gone by, half of the radioisotope decays. If we go for one more half-life, we'll find that half of what we had at the end of the first half-life, so half of m0 will be left, which is the same as 1 over 2 to the power of 2 times m0. After one more half-life, we'll find that half of whatever we had at the end of period 2 is left, and that becomes 1 over 2 to the power of 3 times m0, and this pattern continues. And this is going to lead us to the formula. Mass left, which would be here, mass left is equal to this amount. And after n half-lives, then the exponent of 2 will be n. At the end of one half-life, exponent was 1. At the end of 2 half-lives, exponent was 2. At the end of 3 half-lives, exponent is 3. So at the end of n half-lives, we will have 1 over 2 to the power of n. And of course, that's multiplied by m0. All right, let's take a look at some problems. Problem 1, how many half-lives will have to pass for 20.5 grams of a radioisotope to decay to 3.8 grams? We start with the formula. In this case, n is missing, the number of half-lives. Rearrange the formula and solve it for n. Now, we have seen this rearrangement many times, and so I will just let you go through the logic. Replace m0 and m with the given values. 20.5 is what you start with, that's m0. 3.8 is what you are left with, that's m. Perform the division. And by now you should know how to work this out on the calculator. And you should end up with 2.4 half-lives. Okay, as far as n goes, we can find n if we know the total amount of time that has gone by and also the half-life of a radioisotope. Here's how that works. Suppose half-life is 8 days for the particular radioisotope that we are dealing with. So every 8 days, half of what we start with decays. Now, if 8 days go by, that's the actual time when that goes by. If 8 days go by, that will of course be one half-life, because every 8 days is one half-life. If 16 days go by, we end up with 2 half-lives. That would be 2 of these. 24 days correspond to 3 8 days, or 3 half-lives. 32 days becomes 4 half-lives. And you notice in all cases you can find n if you divide t, total time passed, by the half-life. 8 divided by 8 is 1. 16 divided by 8 is 2, and so on. So the formula that relates the number of half-lives, time passed, and the half-life is n is equal to T over Th. So far we have these two formulas. And of course we can replace n in the first formula with T over Th and come up with a variation of that formula. Some problems may require that you use both of these formulas at the same time, or as an alternative you can use this formula. Problem 2. How long will it take for 45.8 grams of a radioisotope to decay to 33.5 grams? The radioisotope has a half-life of 6.5 days. Now in this case we can solve the problem in two different ways. One is to use these two equations at the same time. We will use equation number 1 to find n, because m and m0 are given. The only thing that's missing then is n. Once we have n, then we'll put n into the second formula along with the given value for Th, which is 6.5 days, to find T. I'll let you work this out. So again, use equation 1 to find n, then use equation 2 to find T, and you should end up with 2.9 days. As a variation, how long will it take for 45.8 grams of a radioisotope to decay to 33.5 grams? The radioisotope has a half-life of 6.5 days. Now we can use this formula in place of the 2 that we used earlier. We are solving for T. Solve for the exponent, and then for T. Now put the values in and work out the expression on the right side. By now we have talked about all the different buttons that you need to push on the calculator to work out the problem, and you should end up with 2.9 days. Thanks everyone for watching this brief video on radiation problems.